question for you is how many people are familiar with this concept, or this term, the theory of everything? That's what I thought. So this is a very popular phrase with the scientific media. That is, the science reporters love to talk about the theory of everything. The idea with the theory of everything is, if we could ever make a unified theory of gravity and particle physics and so on and so forth, and if we knew all the basics completely, then there would be nothing else to learn because we know everything. And I'm saying this is the most absurd reductionist concept that I've ever heard. And it's shameful that it gets associated with physics. And the alternative, so the alternative I'm talking about is emergence. Now, how many people here have a pretty good idea what emergence is? Excellent, because I think it's something that everybody has a sense of what emergence is, but to get people to agree upon what a definition of emergence is not so simple. I mean, there's a vast, in preparing for this, I've been reading through the philosophical literature, and there's a vast academic philosophical literature on emergence. And basically, most of it seems to be concerned with trying to decide what the word means. And so, what I mean by emergence, this is fairly personal, is I want to ask the question, it's a very simple version of emergence, is the whole really greater than the sum of its parts or not? Because if you understand everything you know about the parts, then do you therefore know the behavior of the whole? And I think the answer is obvious, but I'm going to try to defend it. Now, I had to read through some some philosophical literature, so I went to my main source of information of all kinds to find out what the definition of reductionism is. And reductionism is basically the opposite of emergence. It's saying that yes, if you know the components, okay, then you know everything. And it doesn't deny the existence of things which you might call emergent, but it says that it does imply the ability to understand those phenomena completely in terms of the processes from which they are composed. And this is the opposite of emergentism, okay, which is what I'm really talking about, which intends that emergence, what emerges in emergence is more than the sum of the processes from which it emerges. So I would resort now to simpler language that I understand better. Right? That X being the whole is greater than the sum of the pieces of X. That's obviously wrong in mathematics. Right? Maybe what we really mean to say is that the sum of the parts does not imply X, the whole. That is, the symbol double arrow means, it's a mathematical symbol, means implies. When you put a slash through it, it says does not imply. I'm going to use that symbol again a couple of times. It's not quite really what I wanted to use, but as close as I could get in the mathematical sense. Now, it may be that the mathematics, which is the preferred language of physicists, is intrinsically reductionist. And I think that's actually true. Okay, in mathematics, there is nothing in mathematics except the logic with which it's constructed. Right? Period. There's nothing else there. So in some ways, that's one of the reasons that physicists are inclined towards that outlook. Let's look at some examples. So as long as we're starting with mathematics, let's talk about Julia sets. Okay? Julia set is when you plot a complex number, then square it and subtract a constant, and to get a new value, and then do it over again a bunch of times. Okay? And you get patterns that look like this, which don't particularly look so simple. And in fact, there's a somewhat more elegant and complicated version of the Julia set. So this is nothing but mathematics. There's absolutely nothing here except the serial application of the trivial piece of trivial equation. Just run this equation, get a new value for the complex number, run it again. Now this is a somewhat more complicated version of Julia said. I'd say there's something there more than that simple description, right? Something has emerged. It's kind of beautiful, right? I'll put that back up later so that you can enjoy it. But the idea is that something has emerged from that really simple mathematics. This comes back. That certainly doesn't seem to be in the mathematics. Now, going to the physical world, how many people have heard of graphene? It's probably the most talked about material in the world today because it's really cool stuff. It's one single layer of graphene. Right? It's one flat array of hexagonal array of carbon atoms stuck together in that form. That's just the part of simulation. That's the general idea. It has all kinds of interesting properties that make it very useful. The one I would like to focus on, and I don't try to understand this because I don't, okay? But I'll just say that when you cool it down to almost absolute zero, you put on an enormous magnetic field, it behaves in a way that electrons that are doing the conduction in that graphene array act collectively as if they had formed charge carriers that have charges of 5/7 of the electron charge, or 5/8 or 7/9 or 5/2 or twice the electron charge. These pseudoparticles, okay, you could say, well, there's nothing really in the electrons. This is the way it behaves. This is what it looks like. It looks like you have these new kinds of things which don't exist in the particle physics at all. And they have emerged from the complexity of the interactions between these electrons. Now, you could say it's no way that we could ever explain this, but it has actually been explained after the fact. Once it had been observed, and people found an explanation, found an excuse for such things to exist, and they got a Nobel Prize for it, of course. But if you say, I can predict that from quantum electrodynamics, you're wrong. Okay? You couldn't. Neither could anybody else. It could not possibly ever, no matter how much processing power, no matter how much intelligence you had, no matter how much wisdom you had, no matter how much imagination you had, you could never predict that from first principles. Okay? I'm making this as a very strong statement. Right? Explanation after the fact is different from prediction. Okay? Very fundamentally different. It's very important to keep that in mind. Just because you can explain something that you observed doesn't mean that you could have predicted it.
Sorry, Jeff.
Yeah.
Sorry to interrupt you, but when you say it's not possible, do you mean like you have proof that it's not possible?
Proof is very difficult. That's something to make a statement like that. But I can refer to various people like Phil Anderson, who was the most renowned exponent of emergence in physics, who makes a fairly good case that he explains it in more detail why it can't be done. Right?
Because we often have this explanation like given like 10,000 monkeys and infinite time they'll eventually come out.
I'll get to that too.
But so you're saying even if you had your 10,000 monkeys, you couldn't get it?
Yeah. That's my claim. Right? Now, it'll be interesting. We'll probably have a discussion about this. But I'm saying that it's not possible. And there's reasons for that, which are a little bit too technical and complicated for me to try to go through in 15-minute talk. But one thing about Phil Anderson's model is that more is different, but only if you're cold. Okay? Remember the fractional quantum Hall effect takes place at almost absolute zero. And if you look at higher temperatures, which is the same as looking at higher energies in particle physics, for instance, if you go to the limits that were around in the early universe, then you think you have a model in terms of multidimensional strings that are vibrating and moving and rotating and so on. And then those things, when you cool them down, they form the particles of the standard model, right? And if you cool it down further, you get nuclei and atoms, and finally you get molecules and biology and solids, and down here you get fractional quantum Hall effect. And if you get colder, you probably get more stuff. And that was what Freeman Dyson said in his beautiful paper, Time Without End, which talks about what happens as the universe cools off. Okay? It expands and gets slower. Basically what happens is when things get colder, they don't happen so fast. Okay? But that doesn't mean there isn't an enormous amount of richness at low temperature. Right? And in a sense, the emergent behavior is a temperature-dependent phenomenon. So going back to the physical world, the thing is that these individual snowflakes that are all essentially all different, every snowflake is supposed to be unique. You can explain any given snowflake in terms of a standard model if you work at it hard enough, right? But this is an explanation, right? This is not a prediction. That is, you're not going to look at the standard model and say, aha, I'll bet you we'll get ice crystals that will form into these beautiful structures. Okay, they are all unique. That is not going to happen, and it couldn't happen. And there's, in the aesthetic world, there's a somewhat different version of emergence. The pile of bricks do not contain a Frank Lloyd Wright house. And one of the reasons for that is there's something additional in the Frank Lloyd Wright house that is not in the pile of bricks. Named Frank Lloyd Wright. Okay. I'm sure you can all relate to that. Now, but the thing is that if Frank Lloyd Wright could write down a detailed instruction set, exactly what to do with every single brick, in which order and how, right? There's no way that you'd be able to see a Frank Lloyd Wright house in that instruction set. And that's not just a result of limited intelligence. It's intrinsic. Moreover, getting back to the monkeys, if you give a million monkeys a million years in a typewriter, in typewriters, they're not going to type out any of these works. Right? Even if you give them the instruction set, that is, give them the rules whereby you're allowed to combine these letters, that's not going to help. You're still not going to produce any of these works. Maybe, okay, the thing about infinite time, infinity is a long time. Right? And whatever happens in infinite time, it's probably not of any interest. Right? Because we can't really grasp how long infinity is. But in a finite amount of time, it's never going to happen. By the way, I'm making a pitch for this book, Harry Potter and the Methods of Rationality. It's one of the great works of literature. It's about Harry Potter when he gets inducted into Hogwarts as a young scientist, a preteen superstar, genius scientist. And he arrives at Hogwarts saying, magic? That's ridiculous. There's no such thing as magic. There's got to be a rational explanation for all this. And he ends up trying to figure out the physics of how magic works. It makes a science of magic. Which brings me to the question of magical thinking. Right? Magical thinking is sort of the idea that Arthur C. Clarke expressed in his third law, which is that any sufficiently advanced technology is indistinguishable from magic. Which some people really find objectionable, because they complain that it encourages that attitude, thinking that if it's too complicated to understand, we might as well treat it as magic. Okay, that is intrinsically incomprehensible. Right? I mean, if something is magic in the usual sense of the word, it's intrinsically incomprehensible. That is, you can't explain it. Many phenomena that once appeared to be magical are now at least partially explained. Okay, so but until they are, magical thinking is not an ineffective way of thinking about it. It is, we treat most of the things we're interested in as having some magic. And if we stop doing that and say, no, it's all reducible to simple things, we lose something. So my conclusion is that even if the emergent entity is composed of known subunits and their known interactions, it could be predicted to appear spontaneously if only we understood those subunits and their interactions well enough to see all their potentialities. And even if we are able to explain the emergent entity after the fact in terms of said subunits and interactions, until then, it's sensible to treat the whole as greater than the sum of its parts. This has two implications. The first one is that emergence is often temporary. That is, we may have to treat things as magic at first, but then we can work on it, and sometimes we'll find an explanation. Now, this is not the same as prediction, but still, some things that emerge can be explained, sometimes. And the other thing that, so therefore, the emergence is only temporary. After a while, it becomes reductions. The other thing is that it's usually personal. That is, what I can understand, okay, what I have the capacity to understand, the knowledge to put together with my understanding to understand something, is probably considerably less than what you have on certain things, and vice versa. So emergence is a personal matter. Okay? And some people will see emergence and magic and things that other people consider to be boring, just reducible to standard model. And other people won't. And that's fine. So there's some further reading. Shall I go back to the video? Julia said.
That was nice.
Anyway,
Are you called Julia set?
I have no idea.
Wasn't it mathematician last name Julia?
No doubt. Almost certainly.
Thank you. So I want to understand a little bit about why it is temporary and how, so if we explain a phenomenon after a while, does it become part of a different system so that we know now what it means or how it's explained? Or if it is like it's temporary and it's explained because some of its parts or how the system works are actually bended in a way to include whatever was emerging or whatever is emerging. Am I making sense?
Sure. The example I would give is when you're a child, right, you see lots of things happen and you say, wow, that's magic. And some of those things, as you grow up, you learn how they work and why they happen. Pretty soon, you pretty much have a comprehensive understanding of thinking. I mean, comprehensive understandings are not ever complete. They still give you, they push you over the edge where you no longer regard it as being magical, you now regard it as being understandable. And I mean, things you understand can be magical too, in a different sense, in an aesthetic sense. But I'm talking about magical in the sense of intrinsically inexplicable. So that's right.
For you, do you think consequence is a magical thing? Like consequence of something happening, would that be considered like what are the odds of that happening situation? Is that
Well, physics has a thing called causality, right? And it's based, it's really derived from Newtonian mechanics and thinking in terms of classical physics where you have deterministic behavior. That is, classical physics, in principle, this state of the universe at this moment predicts everything that's going to happen in the future. That's not even true classically, actually. It's law. That's just law. But it was a very popular idea for a long time. And so, I answered your question. I lost track.
I'm not sure if this question will work, but I'm curious because things that are intrinsically incomprehensible, not in that context, but also in context in general, can still be worked on and nod with and play with. I'm still curious though, do you think there's the possibility that nature, capital N, universe, capital U, truth, capital T, are intrinsically incomprehensible?
Yes and no. I mean, I think that the incomprehensible pushes into the comprehensible universe gradually. And sometimes the comprehensible universe pushes into the incomprehensible universe. Emergence is the latter, where the things that you say, well, I understand those things. You put them together, you add enough, and all of a sudden you get things, whoa, this is bizarre. How do those things do that? Is the behavior, when the behavior of the combination of things, especially large numbers strongly interactive, when it begins to exhibit behavior that you've never seen anything like it in any of those components, that's physical emergence. And it's true conceptually too. I mean, there's many times where you have a whole bunch of ideas that you suddenly put together and you're running into the world. You have a realization at a level. In the philosophical literature about emergence, there's all this talk of levels, right? And it's instinctively, intuitively, obvious, but it's very difficult to explain. People work really hard to kind of make a rigorous description of what a level is.
Here. Can I ask you a simple question about the Julia sets, because it's about visualization? What, for you, they were confusing to me because you talked about sort of information being put in or theory being tested consistently. Do you know what the visualization is? Like, what is its meaning, or what is its storytelling?
Most of the Julia sets are static. Usually a Julia set, you'll see the static, I'll just do the ones because they're nicer. So those are ones where the constant that's being added is changed gradually, and then you see how the Julia set evolves. But the usual Julia set is a picture of how, if you start at this point, how long does it take for the thing to get completely lost, right? And so they do that over and over again on all these different points, and they make this fractal picture. So it's a typical kind of fractal. I wrote a program once because I thought it was fun. I thought, wow, fractals are cool. And it was just, I just basically did the Julia. I just took plotted it as a dot on my screen, and then I squared it, added a constant, and plotted it as, plotted that as a dot, and then turned that loose and watched it develop in real time. And that makes the most unbelievable pattern of dots on the screen. The edge, and it's in these